Hi, today we are going to solve the third problem of electric field chapter. This time the geometry is still going to be two-dimensional, but now instead of a straight line, we will have a quarter of a circle. So let me write down the question first. So this is the third problem. So it's basically the following. Calculate the magnitude of the electric field at the origin, I'm going to draw the figure for you, so don't worry about the writing, due to a positively charged quarter of a ring. So what I mean by that is the following. Maybe I should draw it here. Okay, so this is the y-axis and this is the x-axis. What we mean is a quarter of a ring, which is thin enough and positively charged. Okay, so like this. Positively charged here, where the radius of this thing is r, so that's r, and the charge of this whole thing is q, plus q. Okay. Okay, so how are we going to solve it? Again, it's the same idea. We just take a very small part of this, infinitesimal we call it, with a charge of dq. It's an infinitesimal portion of this whole quarter of a ring, and basically you can draw that. And obviously I'm exaggerating the thickness of that. Imagine that it's infinitely small. But for the sake of drawing it, let's say it's this big, where the arc length of this thing is ds, okay? And what is the electric field due to this infinitely small guy? And it's going to be basically this, right, dE. And if this angle is theta, it's going to be exactly the same angle here, right? And that's why dE is going to have two components. One is going to be dEx, pointing right, and dEy, pointing down, right? Okay, so that's like the geometry, right? And this is the radius, the same radius r. And the angle that corresponds to the small arc length is d theta. If this is theta, this is like the infinitesimal angle, so to speak. Okay, so let's write it down. So this is a vector, obviously. And let me write down dE first in vectorial notation. So one component is dEx, so that's pointing right, and that's why it's plus I. And that's dEx, right? And the other one is pointing downwards, and that's why I'm writing minus j hat dEy, right? And due to the geometry that you can see, if I make this a triangle, the adjacent one is the cosine one, and that's dEx. So that's why dE vector is equal to plus I, it's the magnitude of the vector, multiplied by the cosine of the angle. For the x component, it's the adjacent one. And the other one is pointing down, that's why again minus j. And dEy is the other component, and that's the opposite side, and that's why it is sine of the angle theta. Okay, so that's that. Now we need to write down what dE is, right? dE is, dE magnitude is the same old 1 over 4 pi epsilon 0, right? And the charge of this guy divided by the distance squared. And the charge of this guy is infinitely small, right? So that's why that's dq divided by the distance squared, which is r squared. Okay? And this thing, I need to express dq, again, in terms of the thing that changes. In this case, it's the angle, right? And remember how we do it? This is, again, a one-dimensional homogeneous charge distribution, right? And that's why dq is lambda times the length of this thing, which is ds, right? Okay, so this thing has two parts. One is what is ds, right? ds, as you can see from the figure, the length of the arc is equal to radius times the angle, right? As you know from the circumference, right? For circumference, it's 2 pi is the total angle multiplied by r gives you the circumference, right? Here, 2 pi is the angle. Here, the angle is theta and the radius was r, so that's why it says r times d theta, radius times the angle gives you the arc length, okay? Good. Now I need to know what lambda is, so I'm going to put another arrow here, okay? Lambda, remember, is one-dimensional charge density. That means it's the charge divided by the total length. So what is the total charge? That's Q. And what is the total length of a quarter of a circle? If it had been the total circumference, it would be 2 pi r, but it's just a quarter of that, and that's why it is pi r divided by 2, right? Divided by 2. It's 1/4 of the total thing, which is 2 pi r, right? And that is equal to 2 goes up, 2q divided by pi r. Okay, so now I'm ready to write down this dq in terms of these guys. It's lambda, which is this, times that, right? So dq is equal to lambda times ds. Lambda is 2q divided by pi r, right? And ds is r times d theta. Okay, this is nice. I can cancel these two. And I'm going to get this better form. 2q divided by pi times d theta. Okay? Okay, so this is all good, right? Now the next thing is I'm going to take that and put it in this equation and write down what this dE magnitude is, right? So the magnitude of dE is the factor in front, which is 1/4 pi epsilon 0, right? And this is dq, which is all of that divided by r squared, right? So that's 2q divided by r squared times pi times d theta. And now I can do a simple cancellation here, or simplification, and the whole thing will be q times d theta, right? So this is q. And in here, the cancellation will give me 2 here, right? 2 pi squared, 1 pi here, another pi here, so that's pi squared, 2 pi squared times r squared times epsilon 0, right? And by the way, as a side note, let me maybe put it here. You can see this relationship, dq is equal to 2q divided by pi d theta, in a simple way, and the way that I would think is the following. It's a simple ratio. What I mean is, like, if the total charge is q when the angle is pi over 2, what is the charge in here if the angle is d theta? So you see, it's actually very simple, right? You multiply this by that and divide by that, and that's what you get here, right? So, but this way of thinking is very important. So I don't want to make you, use these. I mean, you can use the simple ideas and tricks, but you should always know how to do this one-dimensional charge density, and then, just putting everything together like that. You will have like two-dimensional and three-dimensional case. So you need to know the systematic way of thinking in terms of charge densities and charges. But still, it's good to see these kind of things as well, right? Okay, so we're almost done. So this is dE. I already wrote that in terms of things that I know. And now there's cosine and sine, and this is dE. What I'm going to do is E is equal to the integral of dE, right? Which is nothing but the x component and y component, right? This one and that one. So remember that it was plus I hat times dE cosine theta, right? And I have, let me put minus here, j hat dE and these are in magnitudes, of course, times sine of the angle theta. And remember, the range of the integral, it starts from 0 and it goes up until pi over 2, right? If I take the angle as the variable, okay? Now I see that both of them have this factor of q, 2 pi squared r squared epsilon 0 inside d, e, and there's only d theta here. So the whole thing will be the common factor which is going to go out of the integral, q over 2 pi squared r squared epsilon 0, so I'm going to take that out. So that's q divided by 2 pi squared times r squared epsilon 0. That's the common factor that appears in dE. And inside the integral, I have I hat. dE is now only, the remaining term is d theta, multiplied by cosine theta. And the other one will be j, d theta, sine of the angle theta. Okay, good. And let me close the parentheses. And the range is from 0 to pi over 2. Okay, so both of these integrals are quite simple, right? This integral is sine of the angle theta, and this one is minus cosine of the angle theta. And this minus and that minus are going to cancel each other nicely. And electric field will be equal to q divided by 2 pi squared r squared epsilon 0. Now, I had sine theta, you put the upper one and the lower one and subtract one from the other. So I'm going to use the other one just for fun. Sine of the upper one minus the lower range, which is sine 0, right? And then, now this minus and that minus are going to cancel each other, so that's plus j hat. And again, I'm going to use the purple one, right? Cosine of the upper range, which is pi over 2, minus the lower range, close parentheses, okay? So that is 1 minus 0, right? So it's 1 minus 0, and that's 0 minus 1, okay? So the whole answer will be E, q divided by 2 pi squared r squared epsilon 0, I times 1 is I, and minus j hat. Okay, so that is the whole expression for us. Now the question is asking us to calculate the magnitude of the electric field. This is the x component, this is the y component, that's the common factor. You take the square of each, add them up, and take the square root to get the magnitude, right? So E magnitude will be the common factor in front, and then you take the square of each, 1 square plus minus 1 square, and then take the square root of the whole thing. 1 plus 1 is 2. So the whole thing is square root of 2. And this thing cancels that, and it leaves square root of 2 here. Finally, our answer will be the following. Q divided by, here I have square root of 2 pi squared r squared epsilon 0. Okay. And let's take it into box. Okay? Okay, so I hope it was fun, and thank you for listening.